Alright, hey. I wanted to make you guys this video about integration, which we started talking about the other day. I won't go through what's on the screen again. I've gone over this, I think, a couple of times Friday and then again today on Monday for the people that missed it. So if you're needing that basic stuff, I guess come see me and we'll talk. But we went through this, we went through this, we went through this, we went through this. Here is where I think I will jump back in as we talk about how to actually use Riemann sums to find the areas under curves. And there were 4 different types of Riemann sums. There was the left-hand sums, the right-hand sums. There were midpoint sums and trapezoidal sums. Now I got so far as sort of drawing these, but I think we're supposed to actually come up with the area. So let's kind of do this again and talk about it. But it says here that what we're after is the area of this region on the interval from 2 to 8. So if you mark, if you mark 2 to 8, then from 2 to 8, that's a total horizontal change of 6. You can of course find that by just doing 8 minus 2. That tells you the total horizontal change is 6. And it says up here they want us to use 3 sub-intervals. So if I divide this 8 minus 2 by 3, then that's a 6 divided by 3, that's 2. That's a measurement that we're going to want to call delta x. And essentially it tells us how wide we want each of our rectangles to be. But now speaking of rectangles, we know that we would want one rectangle that lives between 2 and 4, the next one between 4 and 6, and the next one between 6 and 8. Okay, so I've just thrown these rectangles in here kind of haphazardly, but what we want to do now is make sure that they all have the right height. Okay, I can drag these guys, drag them up and down. Now the height depends on what kind of rectangle it is. Since these are left-hand rectangles, you want their height to be given by their left-hand side. And what I mean by that is, you would take this rectangle and you'd kind of grow it up until its left side touches the function. So see that leftmost corner right here is touching the function at a height of 6. That's going to be my left-hand rectangle. Now I'll take this next one and I'll grow it up until its left side touches the function. Notice its right side is touching the function right now, but we need to continue up, 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 so that the left-hand side is touching the function, and you see that at 4, that's getting a height of 8 for that rectangle. And this guy's actually too big. We want to take this guy, drop him down until the left side of the rectangle is touching the function. But that's it. Looking at this now, oops, if I wanted to actually find this area, I would just take the area of those 3 rectangles and add them together. Now all of them have a width of 2. We just talked about how to find that width. And all of them have heights that are given by the function. So pretend for a moment this function was called f of x. Then the height of this rectangle would be f of 2, right? Whatever the value of the function is at 2. And we can see that that number is 6. So that first rectangle is giving an area of base 2, height 6. So an area of 12. Oops, base 2, height 6. All right, the next one, this guy's got a height of f of 4. And we see the function value at 4 is 8. So this whole rectangle is 2 by 8. Then finally the last rectangle, his height is given by the value of the function at 6. And we can see that value is the same as f of 2. We're getting 6 again. So that rectangle is 2 by 6. So that means the total area here, or at least the area that we are approximating, is 12 plus 16 plus another 12, which is what, 10, 20, 30, 40, yeah. So our area here is 40 square units. Now depending on what this function represents though, this area could be anything, right? We talked about how to find the units for our area, but for this problem we're literally just finding area, so to leave it as 40 is fine. Now, looking at this, I can tell that I've got much more over approximated area than under approximated area. The first rectangle is under, but the second rectangle is over. Now it's probably over by less than this one is under, but then you've got the next rectangle which is over approximating by a lot. So if we kind of added all these things together, we should definitely be expecting this left-hand Riemann sum to be over approximating. Now if we do the right-hand Riemann sums though, if we drag over a rectangle and a second and a third, then this time we're going to let the right hand side of the rectangle define the function, which actually means this rectangle here, I like to start from the right and go left this time. Over here I started left and went right, but we got to shrink this guy all the way down until the right corner touches the function. That means we just lose this whole rectangle. It just collapses down to a 2 by 0 chunk of nothing, which is fine. That happens sometimes. Anyway, this one will drop down until we're getting the height of the function at f of 6, and it's giving a height of 6. And then this guy, well, he's kind of just right. He's at a height of f of 4, so that's 8. But now to find that area, there's technically 3 rectangles here, so I'll show the work for all 3. But the first one has a base of 2. They all have a base of 2. But the height is this time given by f of 4, which is 8. Now the second one has a base of 2 and a height that's given by the function value at 6, which happens to be 6. And then the next one has a base of 2 and its height is the value of the function at 8, which just so happens to be 0. So in terms of areas, we have a 16 plus a 12 plus a 0. So that's giving me a total area of 28. And so now we can see pretty clearly that the left-hand Riemann sums is over approximating our area, and the right-hand Riemann sums is under approximating our area. So if these left and right-hand Riemann sums are so bad, then why do we use them? Well, we don't, always. Sometimes we use these other approaches. Now to find our midpoint approximation for this area, again I'll drag over my little rectangles. But if I'm looking to define these rectangles' heights by the midpoint, well, the midpoint of 2 and 4 is 3. So you would drag this rectangle until it's sitting at the function value at 3, which is putting me at like 7.5. Then this next one that goes from 4 to 6, well, you'd want to dictate the height of the rectangle by the midpoint, which is 5. So you drop that guy down until it was touching at f of 5, which again is about 7.5. And then this time, the rectangle that goes from 6 to 8 has a midpoint at 7, so I'm going to drop this down until the middle of that rectangle touches the function value. And this guy's height now will be given by the function value at 7, which appears to be about 3.5. But that's it. We just kind of set our rectangles up differently. Now what am I getting for area as I calculate this? Now the first guy still has a base of 2, and his height, we said, seems to be, let's just call it 7.5, keep it as simple as we can. The next one is base of 2 with the exact same height because of the symmetry of our function. We know those two y values are the same, so again we'll call it 2 times 7.5. And then the last rectangle has a base of 2, and we said the height at the midpoint appears to be about 3.5. So that's given me, what, 15 and another 15 plus 7? So that's giving me an area of 37 square inches. And what you might want to remember is from the left and right hand Riemann sums, we got 40 and 28. And those numbers, that does put 37 right in the middle. 37 is a little closer to the 40. It's not perfectly in the middle because it was never meant to be the average of the other two. But notice that 37 is probably a better, more accurate interpretation or estimation than either the left-hand rule or the right-hand rule. But finally, for the trapezoid rule, we're not using rectangles anymore, but we're still going to divide this interval up into 3 equal pieces. And since the width is 6, that means every bit should be 2 units wide. So we'll draw lines at 2, 4, 6, and technically at 8 there's something. But now the way we make a trapezoid is just on the interval that goes from 2 to 4. You're going to want to connect f of 2 to f of 4 with a nice straight line. And we can see that because our graph is concave down, this trapezoid is going to under approximate our area, but that's okay. Between 4 and 6, just do the same thing. Draw another trapezoid. He's going to underestimate our area. And then lastly, this guy isn't even a trapezoid at all. He's kind of just a right triangle, but that's okay. We'll let him be sort of an honorary trapezoid for the purposes of our solution method, because we're still doing the right thing. To form our trapezoids, you just connect the y values at the ends of your intervals, and if one of them happens to be 0 so that you get a triangle, well, that's just the way it goes. So now to find my area, or at least to approximate it, I need to find the area of this first trapezoid, then I need the area of the second trapezoid, then I need the area of the third. And all 3 of them have the same formula, right? All 3 of them are 1/2 times b1 plus b2 times height. Now they all have the same formula, but they're not the same. Now, on second thought, 1 and 2 are the same. So technically I could just write this expression once and double it for those 2. But since that's not always true, since it's rarely true, I think I'll break this down and we'll just have to show the formula all 3 times. So we got 1/2 b1 b2 times h, 1/2 b1 b2 times h. And then the last guy is technically a triangle like we said, but we can still do it like it's a trapezoid. So 1/2 b1 plus b2 times h. And all of these are getting added. So the first guy, he's got that 1/2. Then the b1 and b2 are going to be the bases, and the bases are the parallel sides. So b1 and b2 are both of these function values. So we want the function value at 2, which seems to be 6. Then we want the function value at 4, which seems to be about 8. Then we want the height of the trapezoid, and height has always been the distance between the bases, so that distance is 2. It's the same delta x that we found before by doing interval value minus interval value divided by the subdivisions. So from the interval, if we're 2 to 8, then again, we're going 8 minus 2 over 3 subdivisions. That's 6 over 3, that's 2. So that's what I'm doing here. So my height is 2, is what I'm getting at. All right, what's my next trapezoid? Well, it is literally congruent to the first one. So this will just again be 1/2 times 6 plus 8 times our height of 2. And then what about our last quote-unquote trapezoid? Well, of the 2 bases, one of them is actually 0 because it isn't there at all. So you just go 0 plus this guy's height, which is 6, and then times the length of the base, which is 2. And yes, I get it. We could have just done this with the triangle rule, but I don't know, it's called a trapezoidal sum, isn't it? They should all look like trapezoids. Okay, so what's this coming out to? 6 and 8 makes 14, half of 2 is 1, so that just is literally 14. And the next one should be 14 too, because again, the half and the 2 cancel, and 6 plus 8 is in fact 14. And then this last little guy, half of 6 is 3, and 3 doubled is 2. Half of 6 is 3, and 3 doubled is 6, is what I meant to say. So plus an extra 6, which means this time my area, calculated this way, is 34. Yeah. So, oh my god, degrees. It's not 34 degrees. 34 square units. Alright, I don't know why I labeled that degrees. The only thing I was thinking back to that might have been distracting me is, notice that the 34 is actually more towards the center here. And come to think of it, what is the actual center of 28 and 40? Well, it's the average. So 40 plus 28 makes 68. And if you divide that by 2, oh my gosh, you get 34. It turns out that the trapezoidal rule is for sure just literally the average of the left and right hand summations. So notice if you're being asked to do the left hand summation and the right hand summation, then the answer to what the trapezoidal approximation will just be the average of those two numbers. So if you have them, just add them up and divide by 2. You wouldn't even necessarily need to run through all this trapezoid stuff. But in case you ever do need to do it, I hope you understood. You can ask me later if you didn't. All right, so this thing is important for sure too. I'm definitely going to ask a bunch of quiz questions asking you just to decide if one of our estimation strategies is an over approximation or an under. And again, for an increasing function, just draw the thing. You can see that on an increasing function, if I'm going between 1 and 3 and the height is dictated by the value at 1, well, by the nature of the fact that we're an increasing function means our right hand side would be the taller side. We're definitely using the shorter side, so we're getting less area, so we know that this is an underestimate. All right, and then the same logic applies over here. If we were going from 1 to 3, but this time we're using right-hand Riemann sums, then that's going to be the higher side, and we're going to be getting an overestimate. Now, same thing again here, really. If we're going from 1 to 3, and this time we're using the left side, well, now the left side is the taller side, so we end up getting a rectangle that overestimates. And for the right-hand rule, between 1 and 3, if we let the right-hand side give the height, so I didn't do that right, did I? Yes, I did. I'm great. All right, if I let the right-hand guy give me the height, then we're only getting this. That's back to another underestimate. And then notice that with the trapezoid rule, it's not about whether we're increasing or decreasing at all. It's about whether we're concave up or down. So again, on the same interval from 1 to 3, we can see that if I connect these dots with a straight line to make my trapezoid, that straight line goes over the curvature of the function, and therefore it gets an overestimate. And finally, for functions that are concave down, if I'm going from 1 and running all the way to, say, 4, then as I connect those dots, that line is going to naturally run under the function that is concave down, and you're going to miss a little bit of area, and therefore this is an underestimate. So make sure you know that. Make sure you can determine whether our methods overestimate or underestimate our area based on whether the function is increasing, decreasing, or concave up, concave down. All right, so this was the first actual mathy question. So how does this work? Well, if I'm you, I'm plotting all these points so I can get a better visual idea of what's going on. And on the x-axis, we're going to go 0, 3, 6, 9, 12. Pretty standard. You can just use the numbers they gave you, and that's a nice, easily, automatically spaced scale. Now on the y-axis, we got to put these values, which have a min of 7, a max of 27. Let's just call that max 30. So the top of my graph wants to be 30. Then chop that in half. There's 15. Then if we're going to count by 5s, then cut this into thirds. There's your 5 and your 10 and your 15. Then cut this into thirds. There's your 20 and your 25, all the way up to 30. Now just plot points representing these points. It says that at time 0, water is being pumped at a rate of 7 gallons per minute. So at 0, we go up to 7. That's right about there. 3 is giving 13. So 1, 2, 3, and I hop all the way to 13, which is, let's call it there. Then 6 has us up at 18. 0, 1, 2, 3. What did I not draw enough tick marks? Oh, we're counting by 3s. Okay, so I'm bad at this. I obviously meant to say that's 3 and 6 and 9 and 12, which means I should have plotted this point further over. So this is supposed to be 3 giving 13. That's right about there. Then 6 is giving 18. So that's up here between the 15 and the 20. 9 is giving 23. So 9 goes all the way up to about here. And then 10 gives 27. So you're going up to about here. And then looking at these 5 data points, they all lie pretty nicely on a nice straight line. So if I did my trapezoidal approximation method, would probably get an answer that's really, really close to the truth. But we're being asked to use right-hand Riemann sums first. So before I do that, let me just save this handy drawing so I don't have to do it over and over and over again. But my lovely drawing should go with part B, and should go with part C, and should go with part D, so I can do it over and over. But again, for the right-hand Riemann sum, all of the heights are going to be given by the right-hand side. So first thing still that we should do is just drop a bunch of vertical lines to help build these out. So these are the rectangles we're talking about. And since we're doing right-hand Riemann sums, we'll let the right side give us our height. So the right side would be this value, and then over and down. Then the right side makes the next guy, the right side makes the next one, and the right side makes the next one. This is giving me 4 subdivisions. Is that what we wanted? Yes, it is. So now we're actually supposed to find this area. And again, we would just want to know, all right, well, what's the base of every rectangle? We see it's 3, so delta x is 3. And what's the height of every rectangle? Well, all the heights come from the function values. Now this, I didn't draw this perfectly, but this height is just the function r evaluated at 10. Then the next height is r. Oh, I'm screwing up, aren't I? That ain't no 10. That's 12. My bad. So if that's 12, then we just want r of 12, then we want r of 9, then we want r of 6, and then we want r of 3. And if I just pull those values out of the table, then I've got all the heights here. So my area, according to my right hand Riemann sum, I think people will write that, RHRS. Right hand sum, I think I typically just write RHS. Right hand sum, and we just kind of leave Riemann out of it, I guess. But right hand sum, my right hand sum is going to literally be 3 times, and again, I'm going to start on the right and move my way in, but it'll be 3 times 27, because that's the height of the function at 12. Then you'll add to that 3, because that's still the base of our rectangle. The height of our rectangle is now given by r of 9, so that's 23. Then this third rectangle in from the right has a height that's equal to r of 6, so that's 18. And then finally, this first guy has a base of 3 and a height of r of 3, which is 13. So what's that giving? This looks like 81 plus an extra 69 plus 54 plus 39. So what does all that add up to? Well, I don't know. 81, 69, 54, 39. All right, so that's 9, 10, 19, 23. Put down the 3, carry the 2. 10, 16, 21, 24. So 243. All right, and again, it's area, but it won't do to say that this is square units because we've got more of a context up here. It says that the y values were the rates of change of the number of gallons. So if I integrate the rates of change of gallons, then my new unit is gallons. So that number there represents the gallons of water that we've pumped out. Okay, I don't know if I want to do this a ton more times, but basically now we just do the exact same calculation, but this time using left-hand Riemann sums. That means I'll start on the left, and I'll let the left side of my rectangle give me all my values. So that means this point defines my first rectangle. Then this point defines my second. This point up here defines my third rectangle. This point is going to give us our fourth. And then this guy, well, we don't need him. He's the very biggest. And since we're coming in from the left, we're not going to use that last one. All right, but again, just run through the exact same math. We can see that this time our first little guy here, he's still got a base of 3. But the function value that gives us his height is r of 0. R of 0 is only 7. Then we add to that 3 times, what is it for this guy? 3 is giving his answer, so 13. So he's just 3 by 13. That's too many 3's. Just wipe that out. Okay, the third rectangle has a base of 3 and a height from the 6 giving 18. So base of 3, height of 18. And lastly, we've got a base of 3 and a height of whatever the function value is at 9. So 3 by 23. So you're getting 21 plus 39 plus 54 plus 69. So what's all that add up to? All right, so again, this thing is not a 4, that's a 9. I mean, it's not a 9, it's a 4. But okay, what is this? This is 18, 19, 20, 21, 22, 23. Put down the 3, carry the 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's only 183 now. And those are gallons. So again, I don't want to harp on this, but when you did the right-hand Riemann sums, we got our over approximation of 243 gallons. Now that we're doing left-hand Riemann sums, we're getting an under approximation of 183 gallons. If we average those out, what is this, 40 over 200? This one's like 20 under. So we should be getting like 210. If we average those out, it would be about 210, which wouldn't be a terribly bad approximation. But again, we've got that kind of built in. The midpoint rule here would, it should give us an answer that's sort of closer to the truth. And certainly the trapezoid rule is going to give us a better answer. Now, one thing to notice though is we've been using 4 subdivisions here, but now because we're doing the midpoint rule, we're only down to 2 subintervals, so that would change our delta x. We would still take our interval and we'd go 12 minus 0 divided by number of subintervals, which right now is only 2. So that's telling you that you got to pick your intervals and make them of width 6. Delta x needs to be 6. So that means I would go from 0 all the way out to 6. Kind of put a line here. Then you go from 6 all the way out to 10. It's kind of like our 2 subintervals. They're just blobbing together the first 2 and the last 2 from when we were doing 4. Now why are they doing this? Well, they're doing it because we need to find the midpoints and evaluate them. And if I'm going from 0 to 6, then for sure the midpoint is at 3. And I can pull that value off my table. It's 13. So if the function value at this point is 13, then I can connect those dots and make this guy a midpoint rule generated rectangle. And same thing over here. Between 6 and 10, your midpoint is at, okay, that's still not supposed to be a 10. It's supposed to be a 12. But between 6 and 12, the midpoint is 9. And so that means we would evaluate the function at 9. It's giving 23. But that means we can put a rectangle here whose base is 3 and whose height is 23. All right, and again, this time we're only approximating with 2 subregions. So that means comparing this answer to the others is kind of apples and oranges, but let's find it. My area would be my base of length 6 times the function value at 3, which was 13. So my area would be 6 times 13. And then the second guy, this red guy, has a base of 6 and a height that is equal to whatever the value of the function is at 9. So this middle one matters. So that's 23. So again, what's my base? My base had a width of 6, and this time my height is 23. So that's giving 60 plus another 18, so 78. This guy gives us 120 plus an 18, so 138. Yeah, I think that's right. So that means my Riemann sum is coming out to 138 plus 78. So 16, carry the 1, put down the 1, carry the 1, 2. So 2 on 6. Great. Okay. Okay, I'm back. I don't know where I was. I started falling asleep there, so got a coffee. I think it's time to talk about this trapezoid one. So let's do that. Looking here, we're back to wanting our 4 subintervals. So that means at each one of these points we'll drop a line. Oh geez, that was horrible. We'll drop a line straight down and form rectangles. Again, this 10 is not 10, it's 12. I said we'll form rectangles, but of course we want to make trapezoids. So connect the dots, connect the dots, connect the dots, connect the dots. And you see this is going to be pretty accurate for us, especially if this relationship is actually linear between these points. But how would I do this? Well, you've got the 4 trapezoids, and each one of them is going to be 1/2 times base 1 plus base 2 times height. So taking the first one, the 2 bases are the vertical sides, and for this first one, those heights are given by r of 0 and r of 3. So it's the 7 and the 13. So we get 1/2 times the 7 plus the 13. And the height of the trapezoid is actually the delta x. It's the horizontal distance on the x-axis. So we know that to be 3. So that's the first guy. Then the next guy will be 1/2. And the bases this time are r of 3 and r of 6. So just the 13 and the 18. And the height is still 3, because that's still going to be the delta x. Then the next trapezoid uses r of 6 and r of 9 as its bases, so 18 and 23. And the height is still same delta x, same 3. And the last trapezoid uses r of 9 and r of 12 as its bases, so 23 and 27. Alright, so before you go to do all this math, it might be nice to notice that the 1/2, 1/2, 1/2, 1/2, that's common to everybody. So you could factor that out. And they all have the height in common. They all have 3 in common. So you could factor that out. So what you've got really is just 1/3 times 3 times 7 plus 13. And then plus 13 plus 18 plus 18 plus 23 plus 23 plus 27. At which point it might be convenient to recognize that this pattern is going to work every single time we do this, right? We're going to have, where did I get a 1/3 from? I got ahead of myself. This is the 1/2 from the formula, 1/2, 1/2, 1/2. So these are all 1/2s. But anytime I'm adding up a bunch of areas of trapezoids, they're all going to have the 1/2 in common because that just comes from the formula. They should all have the same height because the height is our base, which is always going to be equal widths. So that's 3. I just called that, I shouldn't have called that the base, because obviously the bases are the vertical parallel sides. But our height comes from, I meant basically the bottom. These delta x is on the x-axis, but those will all be the same. Now look at what's happening in here too. You've got two 13s, because trapezoid 1 and 2 share the 13. You've got two 18s, because trapezoid 2 and 3 share the 18. And you got two 23s, because trapezoid 3 and 4 share the 23. And then you've got just the 1 7 at the beginning. You've got the 1 27 at the end. But it's kind of going to always go like that, right? So you've got the 1 7, then you've got two 13s. And I'm not going to write all this out, but if you're looking for a way to maybe get through this a little quicker, that might be the trick for you to notice. But for sure, let's run through this and get an answer. I've got my calculator handy. Oh, and it just popped up. Perfect. So we want the 7 plus 2 13s plus 2 18s plus 2 23s plus just the 1 27. So there's that. Then that wants to get multiplied by the 3, and that wants to get multiplied by the 1/2. So I'm getting a final answer of 213. And we should be able to say, how do I turn this guy off? That guy? Yeah. Okay. Anyway, if we're getting 213 for the trapezoidal, 216 for the midpoint, and for the left and right we had 183 and 243. So yeah, this feels good. 183 and 243, meaning midpoint should be somewhere between those, and it is. And the trapezoidal approximation should be somewhere between those, and it is. So that's good. Hopefully you understood this process of getting these approximations from a table of values. But let's move into the homework now, and this should now start to go a lot faster. I don't know. Do I cut this off and make a new video? I don't think so. I'll just make a timestamp. Anyway, for this problem, we're back to just wanting to approximate this with kind of basic geometry tactics, but it says here how many people are in the museum after 5 hours. Well, what's this function model? It models the rate of change of the number of people. So it's sort of like what we're looking at is people prime. And we know that if we're doing the integral of the rate of change of people, then the area represents the number of people. So how many people are in the museum after 5 hours? Well, we're assuming people are streaming in and in and in and not leaving, right? The rate of change of the number of people in the museum. Yeah, so if we just want to go from 0 to 5, then stop here. Nothing else matters after the 5th hour. And we see that we're just getting a big old trapezoid, and I would say by now we should be able to do trapezoids. If you don't want to do a trapezoid, then of course you could draw a line here to just do this as one rectangle and one triangle. But we talked about trapezoids. You guys should get that our area is going to be 1/2 times base 1 plus base 2 times our height. And the bases are the parallel sides, which in this case are horizontal. So this guy is 4, and the bigger one is 5. So the bases are just 4 and 5. And the height is the distance between the two bases, which is 100. So this is going to be what? 4 and 5 is 9. I would do half of 100 to just get 50. And so that's giving 450. And my units are people. So that's that. Then they want to know how many people are in their museum after 10 hours. Well, the fact that this thing is coming down, that's starting to indicate that the first few people that came in, they're starting to leave now. More people are leaving than are entering. So the rate of change is starting to go down, 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 down. And then, I guess I lied. This is just people starting to leave. Yeah. And then now you've got more people leaving than entering. So now it starts to go, the number of people in the museum starts to decrease now, blah, blah, blah. But it says how many people in the museum after 10. We just want the whole thing. And just remember that that area that we found in the last part, that's positive because it's above the x-axis. But we can go ahead and use our previous answer. We already know that this whole chunk is 450. So to come up with the answer for part B, we kind of just need to find this chunk, which is another trapezoid. So let's do that. The area would be 1/2 B1 plus B2 times height. And this time one of my bases is only 2 and the other base is 5. But the height is still 100. So this is what, 7 times 50 for 350 people. But really the final answer would be that our area is the light blue bit that's above the x-axis. It's going to be the value of our integral from 0 to 5. And what are we naming this function? P, I guess. P prime. P makes more sense than to call it P prime, even though it's a derivative. But it might be P of t dt. Then we would want to take away from that this negative integral, the one that's below the axis. So that would be the integral from 5 to 10 of P of t dt. And again, this is notation you don't really know, but just to start using it to get you accustomed to it, we know that first hunk of area is positive 450, and the second hunk of area that we found is negative 350. So that means after 10 hours, there's only 100 people in the museum. And that's it. So number 2 is more of the same. This one again is about a particle moving along the x-axis. So these positive areas imply that the particle is moving to the right. These negative areas down here imply that the particle is moving to the left. But the first one says, where's the particle after 2 minutes? So you literally just want that first little bit of area between 0 and 2, which is another trapezoid. And I hesitate to even do any work here because it's so obvious that these are all just little 1 by 1 squares. So we can see our area is 1.5. So I'm just going to write that. It's 1.5. Now we're saying where's the particle though? Well, that's positive area. So it must have moved 1.5 units to the right. Because this time around the meaning of our answers is it's the displacement of some particle. It's some number of units to the right or it's some number of units to the left. Alright, so now it says where is the particle after 6 minutes? So for that we'd have to run all the way out to 6, and that means we now have what I would break down to a trapezoid piece and a quarter of a circle piece. And so all that blue stuff is going to be negative. We already know the pink stuff's 1.5. And we could kind of do the same thing with the trapezoid. I see 1, 2, 3, 4, 5 complete squares and then a 1/2. So this trapezoid is going to come out to 6. Like we ought to be able to see that. But just to give you some more practice, our total area here is going to be the pink area that we already found, 1.5. Then we're going to subtract from that the area of the trapezoid, which if we're doing it for real, our bases are 2 and 1, 2, 3, 4, 2 and 4. And our height is 2. Then we want to subtract from that the quarter circle. So that would literally be 1/4 times pi times our radius squared. And we can see our radius is 2. So we're getting 1.5 minus. That's 6, 12 divided by 2 is 6. And again, we already knew it was 6. We looked at the trapezoid and could see it was 6. But now I want to subtract from that a quarter of our circle. This is giving 4 pi, so a quarter of 4 pi is 1 pi. Which means if we're going to simplify this answer, then 1.5 minus 6 is 4, negative 4.5. And then minus pi. And I guess I would want you to clean that up just a little bit. You'd at least factor out the negative and call it the opposite of. And 4/5, by the way, is 9/2 plus pi. So our big old chunk of area here is the opposite of 9/2 plus pi. And again, our unit here is this is representing displacement. So if we had to sort of interpret this answer, we would say that the particle is 9/2 plus pi units to the left of the origin because it's negative. That's B. And part C says, where is the particle after 10 minutes? And so after 10 minutes, we want to go all the way to the end over here. So suddenly now there's this little baby half triangle of positive area getting added in. And then down here, there's another little trapezoid. Now, is he congruent to this guy? No. He's a little bit smaller. Yeah, okay. But we also have another quarter circle to add in. So what do we got here? I guess I don't know. I guess I'll take my previous answer because we know we've already got the negative 4.5 minus pi. Then we'd want to take away this trapezoid. So taking away more area, this orange area. This time it's 1/2. The base is 2 and 3, so 2 plus 3, and the height is 2. Then we want to take away the orange quarter circle, which should just be pi again. You're subtracting another pi. Then we're adding on this one little baby green guy, which is just half of a unit, so 0.5. But that now should be all the area on the interval from 0 to 10. And if we combine it all as neatly as we can, then what do we get? Well, what is this trapezoid? It's 3, 4, 5. Half of 2 is 1, so that's 5. Then we're adding a 0.5 to the negative 4.5. So that's going to just make negative 4. We've got a pi and a pi, so that's minus 2 pi. And then, of course, this whole thing worked out to just be 5, so we're taking away 5. So that's giving us negative 9 minus 2 pi, which again, I would factor out a negative and just call it 9 plus 2 pi. And then we'll have it be the opposite of 9 plus 2 pi. So that's the answer to part C. All right, so now we got to number 3. It says how much water has been gained or lost during the first 3 hours. And if we're only doing the first 3 hours, then we can see we've lost a whole bunch of water. And this is just another trapezoid one, so we can go through that really fast. So what's it going to be? 1/2, base of 2, base of 3. And then the height of the whole thing is 3. So this is 5 times 3 is 15 divided by 2. So you could give 15 over 2, or you could give 7.5. But you got to give the units. It says how much water has been gained or lost. And we're measuring the water here not in gallons, but in cubic inches. So make sure that when you give your answer, you either give it as a negative or you make sure you stipulate that it's this much water that we have lost. You don't have to call it negative if you say that we've lost 7.5 cubic inches. If you don't want to say that we've lost it, if you just want to say blah 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 cubic inches, then you better make that number negative. All right, Part B wants to know how much water have we gained or lost in 10 hours. So that means we got to go all the way over. And they're just making us do geometry now just to be doing geometry. But what you see up here above the x-axis is a trapezoid with a semicircular bite taken out of it, right? So I'm going to do this all in one thing. I would like to see you writing one equation that models the whole thing. But basically we're looking for a trapezoid, the one underneath the axis. Plus the other trapezoid. But then we have to subtract away the half circle. And if you like all this, well, you shouldn't, because of course I made a little mistake at the beginning. This first trapezoid needs to be negative. So we'd kind of have to put a negative sign on it if we were trying to write an expression. But we've got the negative trapezoid, then we're adding the positive red trapezoid, then we're subtracting away this half circle. Now, we already know that that first guy came out to negative 0.75 cubic inches. 7.5, I mean. Then we're going to add to that the red trapezoid. And that one's going to be 1/2 times, what's his base? Now you'd still consider this part of the base, of course. But we're going from 4 to 9, so that's 5. The other base goes from 3 to 10, so that's 7. And the height going from the between the two parallel sides is 1, 2, 3. Then I need to take away from that our little semicircular cutout. So that's 1/2 pi times the radius squared. The radius this time is only 1. So what are we looking at? We've got negative 7.5 cubic inches already. Then the red shapes up to be 12. Half of 12 is 6. 6 times 3 is 18. So we're adding in 18 cubic inches. Then the green is, well, it's pi over 2. So that's kind of ugly, but that's okay. So if we want to just finalize our answer, then we're taking 7.5 away from the 18, so that leaves us with 10.5 minus pi over 2. And this time, 10.5 for sure. This time wants to be 21 over 2 minus pi over 2, because then we can combine these two separate terms into one term, where the numerator is 21 minus pi, and the denominator is 2. And all of this is cubic inches. So that would be the amount of water that we gained, because this is going to be an overall positive. So in part A, we lost this much water, but in part B, we started to gain water. So we have an overall net positive change. All right, what about 4? So 4 things are different now. In this problem, all you have to do is find the units that these problems represent. So this should be a piece of cake, because to find the units, you just multiply the units that you have. So if we're being measured in milligrams per year, and time t is measured in years, then we know that the value of the integral here would be, cancel, just some straight up number of milligrams only. All right, the next one says G of t is measured in gallons per month. Okay. And t is measured in months, so just like the last one, the months that x is being measured by cancels the months that our y variable is getting divided by, and we end up with plain old straight up gallons. Anything different in this last one? It says h of t is measured in feet per second. So I gotta guess. Oh, no, they switched it up on us. Oh, and it's not feet per second anyway. Oh, I was so hopeful they actually switched it, but no. It's feet per hour, and then the x is hours. So just like the last ones, those things just cancel and we get feet. So not much to say. about 4, 5, 6. Those are pretty easy. Now, I don't know what I'm looking at. Did I renumber these on your paper? I don't think I did. But looking at 1, it says, is this rectangular approximation shown to the right a left hand Riemann sum, a right hand Riemann sum, or a midpoint Riemann sum? And hopefully you can tell, all of these rectangles have heights given by their right hand sides. This guy here is right hand side. This guy here, his height is by the right hand side. So this is obviously a right hand Riemann sum, RHRS, or just a right hand sum, RHS, right hand sum. Don't care which one you use. Right, now they're asking what's the width of each rectangle. And I mean, we could eyeball this, but I want to model the formula instead. The formula for width of each rectangle, first of all, we would call it delta x. And if we're on the interval that goes from a to b, then in the numerator you do b minus a to figure out how long your interval is. So for our case, 5 minus 2 says this whole thing has a width of 3. But then you divide that by the number of subdivisions that you have. So looking at this, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means my width is going to be given by the maximum value of the interval minus the minimum value of the interval divided by my 9 subdivisions. That's coming out to 3 over 9. That's coming out to 1/3. And again, should you have been able to just look at this, I would hope, and say that between 2 and 3, there's 3 equal parts. So that's literally a width of 1 getting divided into 3 parts. So of course it's 1/3. I get it. I get that. If you can do that, that's great. But there might be a reason why you should actually learn the formula. Like for more complicated ones where it's not so easy to see. Or just for a quiz question that specifically and explicitly is calling out knowledge of this formula. So just make sure you know it. Alright, so this one says sketch the following rectangular approximations. So this ought to be good. We want to use midpoint rectangles on the interval from 1 to 4. So what does that look like? If we're on the interval from 1 to 4, then obviously the entire window has a width of 3. They want me to use 6 subintervals. That means each one of these would have to be half a unit. So we need one to start at 1 and stop at 1 and a half. Then the next one should go from 1.5 to 2. The next one goes from 2 to 2.5, then 2.5 to 3. But we can cram in 6 bars as long as we let each bar have a width of only 1/2. Then we can go from 1 to 4. So right away, I kind of skipped over it, but the first thing you should be calculating is the width of each subinterval, aka delta x, aka for this problem, 4 minus 1 makes 3. 3 divided by 6 subintervals is everything should only have a width of 1/2. Now to make sure this looks like midpoint rectangles, you'd want to make sure that all of these guys have their heights given by the values at their midpoints. So let me make these a little bit see-through. Miss this guy. Alright, so I would drag this guy down until our function was passing right through the midpoint of the top. And just do the same with all of them. This guy drops down until its height is given by the midpoint right there. Yep, this guy comes down, would be right about there. This guy goes right about there. This guy goes right about there. So as far as a sketch of what my Riemann rectangles look like, they should look like this. I should see 6 of them. They should all be half of a unit wide, and they should all hit the graph at the midpoints of the top, rather than the left edge or the right edge. All right, the next one is right Riemann sums. On the interval from -2 to 2, they want us to have 5 subintervals, so this time the math comes out kind of bad because the width of my interval, 2 minus -2, is +4, which divided into 5 equal subintervals has us doing 4/5, aka 8 as our delta x. That's not great, but we can make it work. We want to go from -2 all the way to 2. So like I said, that's a total width of 4. And we have to divide that total width of 4 into 5 equal bits. So this just isn't going to work great. We need to be at 4/5. So I guess eyeball it. Just try to be about 4/5 of the way between -2 and -1. Then start the next one. And make sure it's also going about 4/5, which would be, I don't know, here. But just make all of these the same width. So there's 2/5. So this guy wants to be symmetrical over the axis. Then the next one wants to be about 1/5 past the 1, which would leave us with 4/5, getting us to 2. So there that is. These guys aren't perfect, but these should be equal width. This guy looks a little hefty, but that's okay. And we're doing right-hand endpoints, so make sure that your right-hand side is the one that touches. If I put it here, it's my left corner touching the function. We want the right corner to touch the function. So all of these guys need to grow up. On this increasing interval, they should all be over approximations. So go up, up, up. Then this guy's coming up, up, up. And finally, our graph is tilted to now being a decreasing function. So this right-hand Riemann sum, that guy there, this right-hand Riemann rectangle, I should say, he's the only one of the 5 that slightly under approximates, because on a decreasing interval, those right-hand rectangles under approximate. But that's it. There's your drawing. There's your width. We didn't have to go any further, right? Nope. All right, so one more time. Another kind of ugly one. They want 10 subdivisions, which from -2 to 4, that would be 4 minus -2 over 10. That is +6 over 10. That is 3/5, aka about 0.6. All right, so just start pulling rectangles. We want to go from -2. Can I drag this guy down and across? No, I can't. So we'll have this guy face down. So -2, but I only want 0.6 of it, so narrow that up just a smidge. And then do the others. We get another one from here to here. Here to here. And I'll go back and refine this when I'm done. But how's that? We wanted 10. 1, 2, 3, 4, 5, 6. So not even close. This graph may just be a little small for me to try to work on. But we're trying to go by 0.6. And so mine was too big. I'll just shrink them all. Until there appears to be enough room for 10 of these things. It's 6. I don't know how much room to give myself. I need 2 more. 1, 2, 3, 4, 5, 6. I need 4 more. All right, I don't feel like doing this. It gets pretty unwieldy for higher numbers like 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I would need 1 more. And I need to cram them all in and make them fit. This just looks bad. And so don't worry about it. On the quiz, I won't give you 10 subdivisions. Unless the graph was big enough and easy enough to make it look kind of easy. But there it is. There's my 10 rectangles. And these guys are trying to be left-hand Riemann rectangles. So I'm going to bring this up until the left corner is touching. So this guy under approximates our area. Bring that guy up. Bring this guy up. Next, this guy. Bring it up. This guy's pretty good. This guy could come down a little. This guy's pretty good. This guy's going up and up and up. So there's your approximation. Again, this is a little weird because all these areas are negative. So if you wanted to call this an under approximation, that's technically not quite the right word because they're negative. So what we're actually getting is a number whose absolute value is too small, right? But these guys are too small, but this half over here is too big. So this actually should be giving a pretty good approximation of the truth. Anyway, I'm going to stop talking. That was 3, 4, 5. Then we're going to jump to 9 for a hot second. Now 9's actually giving you the... Oh, this isn't 9, this is 8. Is there a 9? No 9. Alright, so for 8, you actually finally have a function rule now. You're supposed to do trapezoidal approximations with 3 subintervals. At least they gave you a nice interval though, because it's 4 minus -2 over 3. That's 6 over 3. So my 3 subintervals, my delta x wants to be 2. So I could get started on that right now. We'll start to just draw some lines. Starting at -2, we can drop a line. Then we know our delta x is 2, so the next one would be at 0, and the next one would be at 2, and then the next one would be at 4. So these 4 lines cut our interval into 1, 2, 3 subintervals, which is perfect. Now you'll connect these dots. So you go from the top of here to the top of there down to the top of there, this guy down to here, and we get our 3 trapezoids. And what's kind of a pain in the butt this time is we know that what we want is we want for our total area to equal the the trapezoid rule. Trapezoid rule was 1/2 times b1 plus b2 times height, which for us, the 1/2 is fine, of course. b1 and b2 are what? b1 and b2 are the values of the function at -2 and again at 0. So you have to evaluate the function up here and see what those y values are. But b1 is going to be f of -2. And b2 is going to be f of 0. We've got to find those values and do that work. All right, what's our height going to be? Our height at least is our delta x, which is 2. So that doesn't change. But this is the area of just the first trapezoid only. Although good news, it certainly looks to me like this other trapezoid over here is just the mirror image of the yellow. So the orange and the yellow should be congruent. And I can rest assured on that. I hope you guys can too. But that means this orange guy is again just going to be 1/2 of whatever f of -2 is giving plus whatever f of 0 is giving, and then times our height, which is technically horizontal and is the delta x of this problem, so 2. And then lastly, we've got one more trapezoid. It's this guy in green. And that guy will use the formula one more time. We'll go plus 1/2 times b1. I like that to be the shorter one. So that's going to be the function value, f of 4. Then we'll add to that the function value at 2, so f of 2. And we'll multiply that by the height of the trapezoid, which is the delta x, which is 2. But that's it. This is all of the 3 subregions, and I just need to add them up. But before I do that, I need to actually know these function values. So we got to kick it up to the function and substitute in. So we're getting 1/2 of f of -2. Well, -2 squared is positive 4. Quarter of positive 4 is 1, and 6 minus 1 is 5. Now, is our graph good enough that we could have read that off? I would say, yeah. At -2, I can run up. Here's my function. It certainly seems to be that the function is giving 5 there. But we did the math, so we know for a fact that we're good. Now, what about f of 0? That should be an easy one, because we get 0, and 6 minus 0 is 6. And then we still have our width of 2. Now next, this time we want, I guess I said -2, I meant +2 here. But f of positive 2, it should be the mirror image of what we got at negative 2. Negative 2 is giving 5, so let's see if positive 2 is giving 5, like I think it is. Positive 2 squares to make 4, and a quarter of 4 is 1, and 6 minus 1 is indeed still 5. And f of 0 is still 6 from the previous one, and delta x is still 2. And then for our little green guy, we get 1/2 of f of 4, and it certainly looks like f of 4 is just giving 2. Did we use him anywhere else? No. So let's do the math. If you plug in 4 squared is 16, a quarter of 16 is 4, and 6 minus 4 is 2. So eyeballing that value, it seems to be 2, but we checked it in the function. We know for sure it really is 2. Then what's f of 2? We already did that math. We know it's 5. And all the delta x's are 2. So this first yellow trapezoid is giving 11. The next guy that we decided is congruent to the yellow, the orange, he should be 11 also. And then just this green guy is, well, half of 2 is 1, 5 plus 2 is 7, 7 times 1 is 7. So we're getting 22 plus 7, which is 29. 29 what? Well, we are back to just approximating area. Now I don't know what these units are. Is this a foot by a foot, an inch by an inch? Well, it doesn't say, so you need to just call this 29 square units. There's no context to this problem. We're just finding an area, so just give it to me as square units. All right, and then the last few. This time they were so kind as to give you a picture, so that should help you kind of plan your attack. But we want to go from -2 all the way to +1. We want to do it using 3 subintervals. So this math is messy again, because if we do 1 minus... Oh, that math's not messy. Sorry. This math's easy. But we're going to go 1 minus -2 and divide that by the number of subregions. That's going to help us get our delta x. So in the numerator, you're getting 3. In the denominator, you're also getting 3. So this is actually the easiest possible outcome for all of our width, is to just let everybody have a width of 1. But now we're doing right-hand Riemann sums, so work in from the right to the left, and let the right side function value give you your height. So this guy here is going to be an under approximation, but this next guy is slightly an over approximation, and this next guy too. So all in all, we should be getting an over approximation of the answer. But let's hop to it. Our area is just going to be base times height, base times height, base times height. And the base of all these rectangles is the delta x we calculated, which is 1. And the height comes from the function. Now this first guy here, which has its right hand side is at -1 and its left hand side is at -2, we're doing a right hand Riemann sum. So we know we want to get this guy's height by plugging -1 into the function. So our height is f of -1. And we'll find that in the next step. But for the next rectangle, our base is still 1. And our height this time is f of 0. That would be the right hand side for the middle rectangle. So we want f of 0. Then our base should still be 1. And our height is now given by the value of the function at 1, so f of 1. Alright, so what's f of -1? Well, plugging in -1 squares to give 1, so it ends up being √8. And I'd leave that alone for now. Then f of 0 is giving square root of 9, which is 3. So that's just 3. And at 1, the function's giving √8 again, because we plug in 1, we get that √8. So we get another √8. And that means my sum here would be, I would put the 3 in the front, and then the 2 √8. So it's 3 plus 2 √8. Well, that's an x. And what are my units here? It doesn't say, so this should just be square units. All right, but technically, root 8 is a simplifiable radical. Really, these root 8s are both 2 root 2. So if we're going to stick to fully reducing our answers, then what we really have is a 3 plus 4 root 2s. That answer is technically better. So you should give that. Okay, second to last problem? No, this is the last problem. So they want us to do the left-hand Riemann sums with 4 subintervals on the interval that goes from 1 to 3. So if I'm on this interval that only goes from, that only goes from 1 to 3, then that gives me a change in x that's only 2. And I got to divvy up these 2 regions into 4 regions. So obviously all my little rectangles need to only be half of a unit long. So if I connect that, bring up the 2, then that is now 4 divisions on my interval that goes from 1 to 3. So we're looking good. Now we want left-hand Riemann sums. So that means all the heights will be given by the left side. So this guy will be short. This next one will be shorter. This one is short. The next one is, oh, that's the end of the game? No, one more than that guy. But so we're after all of these little rectangles. And again, we said that our delta x is 1/2. Again, if we want to find the area of all these rectangles, we're just going to do base times height like we did before. And I don't mind maybe cutting to the chase here. So my base, if I'm doing base times height, is going to be 1/2. And my height is going to be given by f of 1. And so if I evaluate this function at 1, then I'm getting 1/2 times 1 minus 1 plus 1 plus 2. So -1, +1 cancel out. And you get 2 plus an extra 1/2. So that's 5/2. And that's at 1. So that's my first height. So 1/2, 5/2. Then the next rectangle still has a base of 1/2. And its height is, well, it sure looks like 3, but let's do the math on it again. We want 1.5. You know what? Maybe let's not do that math. Or let's just get our handy dandy calculator. Because, of course, we can do this in the calculator. This guy. All right, there's the calculator. Not the way I meant for it to be. But there it is. If you want to get all these heights of the rectangles fast, you should know the drill by now. We go into y equals, and we substitute the function. So 1/2, or 0.5, x to the third minus x squared plus x plus 2. And you can hit graph if you want, but we're not really trying to see the graph, especially me at least. Zoom 6. If you typed it in right, you should see this basic kind of cubic function shape, but really what we want to do is just see the values that we need. So we could ask this thing, what's the deal at 1? And then we could ask it, what about 1.5? What about 2? What about 2.5? What about 3? And 3 is the last number we would need. But here's all these numbers. The main problem here is it does not give you the exact values. So that's a little annoying. So, do I choose not to care? Or do I choose to care? I don't know. There's my cursor. All right, let me get those values back. We'll just use the decimals because I just want to finish this off. But my second rectangle should have a base of 1/2, and it should use the height at 1.5, so 2.1875. or 2.18 if we're rounding. The next one is again a base of 1/2, but this time the height that we're getting is the height assigned to x equals 2, and we can see that's giving 4. And then for our fourth interval, we still have that base of 2, but our height is now given by f of 2.5, which is 7.313. But you're being asked just to find these 4 areas of these 4 rectangles. So whatever this is, just do that math. It's going to be 1/2 times the sum of all those numbers we just found. So there's no super great way to do that. I'm just going to have to type it in. But 5/2 is 2.5, and then 2.188, and this is half of 9 or half of 4? Half of 4. Half of 4 is 2. Oh no. Alright, so the half of 4 is 2, and then you get 1/2 times... Oh no, I'm not supposed to be chopping these in half. No, I'm supposed to chop these in half at the end. Forgive me. That stays 4. And the last guy stays 7.313. Yeah, okay. So if I press enter, that should be the answer. I'm getting 16.01. Can bring it up for you. So when I add all that up, I'm getting 16.01, which really means it's exactly 16, just with some round off error. So when we added up all that stuff, I guess we must have gotten a 32 here, because then half of 32 is going to give us our 16. And what's this thing represent? I don't know, but our answer is 16. All right, I think that's it. So for sure, you guys, if you're trying to be ready for the test that's coming, definitely make sure you know this page that I don't think I've... Oh, I did fill it out. Great. This one that... Turn this off. This one that, helps you to remember when the left-hand Riemann sum underestimates versus when the left-hand Riemann sum overestimates. It has to do with when the functions increase, decrease. And when the trapezoidal estimation is an over or under approximation, that's concave up or down. So know that. Then for sure be able to come up with values of integrals using basic geometry. You better be able to do that. You better be able to come up with the value of an integral from just a table of data. You could turn the table of data into your own sort of scatter plot and work off of that, but that's something you should be able to do. And then the big thing, right? The big idea is eventually I'm going to give you an actual function. So maybe it's a mixture of these. No, I mean 8's a good example. You'll get the function rule, but you'll also have a picture to look at. And between having a picture to look at and an equation to work with, you've kind of got everything. You should hopefully be able to stay on top of it all and then arrive at some answer at the end that you may or may not need to interpret. So make sure you're able to do the calculations and then make sure you're able to interpret the calculations. Anyway, hopefully this was helpful. Talk to you later. Bye.